want us to start? Should I start with the introduction?
No, I'll start.
You'll start. Thank you very much. Thank you for saying that's right, Don. Thank you.
We are live now on Facebook.
Okay.
We can start.
Yeah, okay, thank you. So, namaste and a very good evening to one and all. On behalf of Institute of Climate Change Research at the Maharaja Sayajirao University of Baroda, I extend a warm welcome to all of you for this webinar. We actually started with a series of webinars with a mathematical background because as I have been mentioning that although climate change is a field which has affected almost all aspects of our life, but when it comes to research in the field of climate change, mathematics has a very important role to play in the research. And I welcome on this panel of webinars all the distinguished guests and the speaker for the day. So welcome Dr. Professor Colin, please, Professor Matty Helio, Professor Chris Budd, the speaker of the day, Dr. Amit Apte, your lecture was excellent, Professor Rachi, and Professor Dhanesh Patel, sir, as well as all the other participants who are with us, not just on this platform, but also on the two Facebook pages, that is the Facebook page of Institute of Climate Change Research, as well as the Facebook page of the Maharaja Sayajirao University of Baroda. So as you know that we started this series of webinars with the first speaker, Dr. Amit Apte, who was from the International Center for Theoretical Sciences, Tata Institute of Fundamental Research, and his talk was on merging dynamics with data, a mathematical perspective on climate change. We then had Dr. Kaurane, who is the president and CEO of Arbonet Limited, and his talk was on modeling climate change with remote sensing of forests as a mathematical challenge. Along with him, we also had Dr. Jarno, who is the head of the unit for RED Plus and sustainable forestry at Arbonet Limited, and his talk was on mitigating climate change by implementing RED Plus programs. And in the series, today we have the concluding session where we have Professor Chris Budd, who is a professor of applied mathematics at the University of Bath, and he's also a professor at the Royal Institution of Great Britain School of Mathematical Sciences, United Kingdom, and he will be talking on mathematical models of climate change, the good, the bad, and the ugly. So before I request him to start his talk, I also have the pleasure to introduce Professor Colin, please. He is a professor in applied mathematics and the director of EPSRC at the university, lecturer in industrial and interdisciplinary mathematics at Oxford Mathematical Modeling Battery Group, University of Oxford. So I will request, thank you, sir, for accepting our invitation to join this platform. And I request you to introduce the speaker for the day along with your expert comment. Dr. Colin, please.
Namaste. Thank you very much. I'm very excited to go and introduce our speaker for this afternoon, Professor Chris Budd. His background is that he started his mathematical career in Cambridge. He then moved to Oxford to do his doctorate and stayed on in Oxford to do postdoctoral work. Following on from that, he moved to Bristol for a lectureship and then moved to Bath, where he's now the professor of applied maths. Chris is particularly passionate about connecting the power of applied mathematics to practical problems, as we're going to hear. And he is a fantastic popularizer of mathematics to the public, and he's a major force in promoting methods that create collaboration and interaction between mathematicians and people in other disciplines. As a result, he's had a number of accolades he's been given. In the year 2000, he became chair of mathematics of the Royal Institution of Great Britain. And then in 2016, he became the professor of geometry at Gresham College. And can I encourage anyone on this webinar who wants to hear other work by Chris? He has a most fantastic set of public lectures on the Gresham College website. I would suggest you all go there to see how he sees the world and how important mathematics is. He's also very active at Bath with many different things, the Institute of Mathematical Innovation and the Interdisciplinary Centre of Nonlinear Mechanics, both at Bath. And he's also worked on a lot of activities connecting mathematicians to problems, working on international study groups, and he's now even working on ideas of how to make virtual study groups. How can people work virtually? So much of this effort has gone on that in 2015, he got what I view as an extraordinary recognition of his services to science and mathematical education when he was awarded the Order of the British Empire, the OBE, in the Queen's Birthday Honours List. Well, Chris always gives really informative, really stimulating and entertaining talks. And so I'm looking forward to the insight he gives us in the talk he's going to give today, entitled The Mathematics of Climate Change, the Good, the Bad, and the Ugly. Chris, the floor is yours.
Thank you very much, Colin. That's very generous of you. I should say that Colin and I have known each other for a very long time. He's a great colleague, and I'm a pleasure to be a friend of his. So let's just check we can see this. Hopefully you can now all see my presentation. So I'm going to talk about mathematical models of climate change, the good, the bad, and the ugly. And what that means is I'm going to have a look at some of the ways that as mathematicians we try to model the climate. And the way that this talk will work is that I will start with talking about the motivation for having these models. I'll then talk in some detail about some of the ways that practical climate models work. And then I'll finish off talking about some of my own investigations, in particular looking at mathematical models for the ice ages. So what's the motivation? Well, our climate is changing and it matters. So here is a famous graph from NASA showing the mean temperature over the last 150 years or so, and the Earth's temperature is rising. And in the last few decades, it's been rising very rapidly. And we are seeing the effects of that in a large number of extreme weather events. Other indicators that the climate is changing is that sea level is rising. It's going up at an average of 3.5 millimeters per year. This is due partly to ice melting, and also as the oceans get warmer, they expand, and therefore sea level rises. We also see the clear effects of climate change on the Arctic. So the amount of ice in the Arctic is rapidly decreasing, and there is a very real possibility that we'll have no Arctic summer ice by the year 2030, which is a very worrying trend. Now, whenever I talk about climate, a lot of climate skeptics say, yes, the climate is changing. It's always changed, so what's new? And that is true. Here is the climate over the last 500,000 years, as measured by looking at ice cores and proxies in the ice cores, which allow us to measure temperature. And the top two graphs show temperature measurements, and the bottom shows the actual ice volume. And we can see that over the last 500,000 years, the climate has had a sort of clockwork variation with around about 100,000 years between warm events punctuated by ice ages. And in fact, what we'll look at the end of this talk are various models for how we can predict why you get 100,000 years. So it is certainly true that the climate has changed a lot in the past, but it's changed in the past over tens or hundreds of thousands of years. And what is so significant at the moment is that we're seeing change over tens or even shorter periods of years. And it is that rapid change that we don't really know how to deal with, or whether the Earth can actually respond to it in a stable way. And that is why we need to get on with modeling the climate and seeing where it's going. But at the same time, we should be testing our models against past climate to see whether they work in that environment as well. So the major centers, the main climate centers, it's their business to try to predict future climate and to inform the IPCC of this. And here are various predictions of the climate from various climate centers around the world. And I should say that the climate center that I particularly work with is the Hadley Center, which is relatively close to Bath University, where I am. And in this, all of the climate centers are predicting by the year 2100 a rise of at least 2 degrees centigrade, and some are predicting up to 5 degrees. The variation in the predictions largely dependent on how much anthropometric progenic CO2 is in the atmosphere. It's interesting to see that the American prediction, which is the blue one, is the lowest. The Japanese prediction, which is the brown one, is the highest. And the supercomputers at the Hadley Center have added those two predictions together and divided by 2 to get the prediction from theirs. So there we see the full range of predictions. And what I want to do in this talk is talk a little bit about where these predictions come from, how reliable we think they are, and how we can test things against past climate variation. It's important to say, and we know this as mathematicians, that no model is perfect, and that any prediction must come with a level of uncertainty. And here is a graph produced by the Hadley Center showing the mean prediction, which is kind of in the middle, and the various uncertainties due to the computational method, due to the modeling, and due to the overall context that everything's been done in. And it's incredibly important when we do climate modeling and we talk to policymakers that we do talk about the uncertainty. But we do have to be careful. I've found when I talk to the general public and say, well, our models are uncertain, then there's the impression that we don't know what they're doing at all, and they tend to get written off. And so we do have to be careful when we say our models are uncertain. We know what we mean by uncertainty, and we need to quantify that. But at the same time, we should be confident enough to say, well, the models are definitely predicting a temperature rise of within a certain range, and not be ashamed in saying that. But all mathematical modeling, of course, of climate must combine a prediction with a level of uncertainty. Otherwise, we're not being honest with the people that we're advising. So let's have a look at climate models. Modern global climate models are very highly complex. They have billions and billions of degrees of freedom, and they take large computers to run. And I think it's fair to say that when you're modeling the climate, that's only part of kind of modeling the physics, which is kind of what we tend to think of as mathematicians, the atmospheric processes and the oceans and so on, is only part of a much broader set of modeling that we need to do. So climate models must be linked with integrated assessment, where you're looking at the impact of climate on energy, health, and so on. And then all of that, we need to worry about how it impacts on the human condition. So it's really a really tricky thing. I would argue in this picture here that the blue box, the climate models, is the most certain of this. The red is less certain, the green is completely difficult and uncertain. And in my own research, I work on the blue bit, but I'm also particularly interested at the moment of the impact of climate variation on agriculture and also on energy. And I have a group at Bath working in precisely this area. So that's the sort of the general way a global climate model works. But a global climate model is only one of a whole range of climate models. So a GCM, an AOGCM stands for an atmospheric and ocean global climate model. That is sort of one of the highest levels of complexity and comprehensiveness in taking everything into account. And the problem with such models is they are highly complex. They take a long time to run. And in practice, you can't predict the climate for much more than a few hundred years at most using a GCM. So to really get a kind of more general understanding of the way our climate works, we also have to work with models of less complexity and which are less comprehensive, but are still very useful. And in this talk, I'm going to talk about the EMICS and the EBM models as part of this process of a kind of whole range of climate modeling. So just to kind of summarize what they are, so a GCM is a global model of climate, which is complex with millions of lines of code, looks at the whole Earth, the atmospheres and the oceans, and is effective for precise predictions with over decades. And in this talk, I talk about models, the good, the bad, and the ugly. I'm afraid I regard these models as somewhat ugly. As I say, they're very large, they're very complex, they're really quite hard to test. And I worry about how many errors there may be in the billions of lines of code associated with them. But these are the ones that we use to inform the IPCC. The next range down, the EMIC models. These are the intermediate models of the climate, and they essentially try to model as much of the physics as they can. They often treat the Earth as a series of boxes rather than going down to the kind of level of refinement that the GCMs do. And they are able to make predictions over much longer periods. And EMICS kind of are intermediate in the sense that they tend to be a little bit too complex to do full mathematical analysis on, but still comprehensive enough to be useful for predictions. And we'll have a look at some of these in their ability to predict things like ice ages. And one of the great merits of the EMIC models is that we can use them to sort of help validate the global climate models. So if a global climate model makes a prediction which is very, very different from an intermediate model, then we might suspect that the global climate model is doing something wrong. And then the simplest models, these are the ones I teach my undergraduates, but are still very useful, are the energy balance models, the EBMs, which treat the Earth as a single point and look at balances of energy and other things. They're quite good for sensitivity calculations, and because they're so simple and straightforward, there's not a lot that can go wrong with them, and therefore they are, I find, useful for talking to policymakers about in terms of how we model, how we can make predictions. So there's the kind of range of models, and this is where the joke of the good, the bad, and the ugly comes from. So the bad, I'd say, is the EBM. I would argue EMICs are good for mathematicians, and GCMs are a bit ugly when you do that. But of course, that's a somewhat subjective judgment. This is what I do in the day job, as it were. I collaborate very closely with the UK Hadley Centre, and a large amount of my work is done on writing numerical algorithms to make their codes work faster, doing things like adaptive multigrid and so on. And on the right, the circle shows the latest codes that are being used by the Hadley Centre. In particular, HadGem 3 is one of the main codes that's currently being used for the climate. And that has a grid length of around about 50 kilometers and can predict up to 100 years. On the bottom left are the other types of code that I work with a great deal, in particular MOGREPs, which are the codes that are used to predict the weather. And any climate forecasting code is a weather forecasting code plus lots and lots of other things. And that's one way of validating things. Though, as I often say, when you do a weather forecast, you know in 24 hours whether it's right or wrong, and that's a good honesty test. Whereas with the climate forecast, you have to wait 100 years sometimes to see whether it's right or wrong. And most of us can't wait that long. But I'll have a discussion a bit later on how you validate these models as part of the process of designing them. But as I say, that's what the Hadley Centre uses, and of course all the other global climate modelling centres will use similar types of code. So it's a truism, I think, to say that modelling the climate is hard. As Niels Bohr so aptly said, it's difficult to predict anything, especially in the future. And in climate modelling, there are good reasons why prediction is hard. Firstly, a lot of the data that we need has many variations in it, and it's hard to measure. Secondly, we know very well that climate systems are non-linear and can be chaotic. And one of the most frequent objections that I get from people that know something to any sort of climate modelling is to say, well, we all know that the weather systems are chaotic, so how can you possibly predict anything about the climate 100 years into the future? To which, of course, the answer is we're not trying to predict what the weather is on any day 100 years into the future. We're looking for general trends. It's also, we're dealing with a very complex system. I think even now we don't really know all of the influences on the climate. There are things going on deep in the oceans which are clearly having some sort of impact on us, and we don't really know what they are. And so we have to be honest with that. Then there's the distinguishing between cause and effect. And a classic one is, is temperature caused by a CO2 rise, or is a CO2 rise caused by temperature? And this is an important debate, and we have to be very, very careful because they're so tightly coupled that each one leads to the other. But that simple fact can lead to a lot of emotive debate amongst the climate skeptic community. And finally, distinguishing between natural and human-made variation is not always easy. And this is the issue about the climate varying. Yes, the climate has varied over billions of years due to natural variation. But I think it's very clear that the variations in the last few years cannot just be due to natural variation. They must be due to human activity that's simply happening too fast. But this is a point that we need to make. But the fact that climate modelling is hard and there are uncertainty has led to a lot of debate and a lot of kind of almost hysteria in the press. I don't know what Indian newspapers are like, but British newspapers can be very shrill when they talk about climate change. And this is the Daily Express, which is not noticed for being a friend of climate scientists, giving two examples. There are two headlines showing why the British press sometimes doesn't agree with the predictions of climate scientists. The one on the right, the big climate change fraud, followed the hacking of the email accounts of the Climate Centre in Norwich and the misinterpretation of some of the emails. But I see all this myself in my own work. As Colin said, I'm Gresham Professor of Geometry, and I've posted up a number of talks about climate change on the Gresham College website, and that attracts a lively correspondence. And these are some of the comments that have come onto my videos. I should say these are the polite and knowledgeable comments. There are a lot of rather less polite comments there. So you might like to just enjoy these. I've already mentioned the climate's always been changing and everyone blaming it on the sun. My favorite one is at the bottom, where someone said, it's rubbish. Maths is all about, quadratic equations. It's nothing to do with the climate. Don't you agree with that? And that was kind of led to an interesting correspondence. But despite all these uncertainties, I still argue and say to policymakers whenever I can that mathematical and statistical modelling is still our best tool for understanding what's going to happen to our climate. By far the best technique. Firstly, and of course we all know this as mathematicians, it allows us to be objective in our analysis and understanding. We can understand the sensitivity. So things like people will say, well, 2-degree of warming, how can that possibly be important? You know, you vary more than that during the day. But the key thing is that if you move the average by 2 degrees, so the tail of the distribution rises, and therefore you get far more extremes you know, far more extreme weather. And it's only mathematical modeling, I feel, which can make that clear, that a small average change in temperature can lead to these things. And this is something we have to get across. And of course, climate models can be practically useful. What I'm doing in my research at the moment is working with the National Grid Company in the UK, taking the climate predictions over the next 50 years from the Hadley Centre and trying to work from that to understand the impact on our energy network in the UK. So all of these reasons are excellent reasons why we should persevere in doing mathematical modelling of climate, despite all the difficulties that we know are inherent in it. But there is another reason, which I wouldn't tell policymakers, which is actually mathematical models of climate are genuinely interesting things to study mathematically, and we can learn a lot of nice mathematics by studying them. And I'm sure that came out in the previous seminars in this series. Okay, so I'm sure many of you are familiar with this, but for those of you who are not so familiar, I'll just run you through the process by which modeling works. Sorry, go back to this. I know I'm a mathematician, of course, but we all start climate models with the laws of physics. We formulated these as partial differential equations. We incorporate data. So Professor Apty, I'm sure, talked a great deal about this earlier on. I know he's an expert in data assimilation. We have to build in uncertainty into all of our models, and no climate model other than the simplest energy balance model can be done analytically. So all must be solved numerically. What makes up the climate? Well, the first set of things that I put here are the things that you put into any weather model: air pressure, air velocity, ocean temperature, air density, moisture, and clouds. And then to build into a climate model, then you have to incorporate many other things, such as ocean salinity, behavior of the ice, changes in solar radiation, the effects of human activity, and so on. And combining all those into the Navier-Stokes equations then gives you the fundamental partial differential equations, which are used to predict the weather. And what I have there are very much the equations that are used every day in the UK Met Office and every other Met Office in the world to predict the weather. And as I say, these equations are extremely well tested, and the models are verified every day for their accuracy. The hard thing for climate is to add in all the other effects. And here's just a sort of summary of the way that things have been added into climate models over the years. Again, I've taken a somewhat Hadley Centre perspective, but I'm sure other models are similar. So in the 70s, the models just dealt with the atmosphere. In the 80s, they built in land surface and oceans and so on. But now, if we go to the far right, you can see the way that chemistry, atmospheric and ocean chemistry and ice effects are in the current models. And then at the bottom, you can see other models which are being developed to try, to feed in to the way things are being understood. So they are, these incredibly complicated things building in all these different effects. And some of these effects are decidedly difficult to model and also decidedly difficult to verify. And that's another reason why I call these models a bit ugly, in that they are hard to test and hard to verify, but obviously have to include all of this science to be reasonable. This is then my business. We then discretize the PDEs and solve on a supercomputer. And the current HADGEM models go down about 5 kilometers into the ocean depths, up to about into about 40 kilometers into the atmosphere, and you discretize and solve. And we're constantly trying to update the sort of algorithms that we're using so that we can run them faster and more reliably. It's a bit of a joke nowadays that the current supercomputers are doing so much computation to solve these models that they get very hot and are actually contributing materially to global warming. So we have to be a bit careful how we do that. One of the constant objections that I get on my in the comments on my website is that, and I quote, "Climate models are always wrong. Every prediction made by a climate model is wrong." This is what people say, and this is actually completely false. And climate models, of course, have to be tested before you run them. And one of the most important tests is hindcasting, where you test them on past data. And what I've got here is a picture from the IPCC. And the top left, you see the observations over the last 150 years or so in red. And the grey is what the models that we've been describing would predict if you switched off all the anthropogenic effects, so things like carbon dioxide added into the atmosphere. And you can see that the model without those massively underpredicts the temperature that we see. On the right, top right, you can see the model including anthropogenic effects, but not putting in the natural effects like volcanoes in particular and El Nino effects. And you can see that that's much closer to the truth. And the bottom, if you put in the natural and the anthropogenic effects, then you get something which is actually pretty close to the truth, with the model and the observations agreeing very well. And I think the top left picture is very telling, because it's saying, look, if we didn't have human activity, then the temperature anomaly would be about 0. In fact, it's much higher than that. And that, to my mind, is absolutely clear indication of the impact of human activity. And the middle picture at the bottom is clear indication that the models are doing the right job. Even simpler models do the right job. Here's a prediction which was made back in 1981 by Hansen in Science of the increase in temperature on a simple energy balance model, which by and large got the prediction right. And here are the IPCC projections of the rise in sea level based on their models, which are again within ranges of uncertainty, getting things right. So although it's very, very hard to validate a climate model or one of these GCMs over hundreds of years, which we need them to, we can at least say that they are giving good predictions over the decades that we've been able to test them on. And that is a good way of countering the people's objections to saying that these models don't ever get things right. Okay, so that's the kind of what I quote as the ugly models. That's the big models which are being used by the IPCC. But what are the sort of models that as mathematicians we can sort of study as a way of both analytically seeing what the sensitivity to the atmosphere is and also making predictions over much longer time periods than the GCMs? Well, the simplest model of all is called the energy balance model. And arguably this goes back to the 19th century and to Arrhenius. Many of us will be familiar with Arrhenius in terms of chemical reactions, the differential equations for that. But he studied the Earth as a single thing which absorbs radiation from the sun and gives radiation out. And here's a picture which shows the various types of radiation that are coming. So you get incoming solar radiation, which the mean value of that across the Earth is 342 watts per meter squared. And then the Earth reflects that, and also some gets absorbed and then re-radiated. So essentially the simplest models for climate treat the Earth as a single body being heated by the sun and radiated out. What's the process here? Well, we get incoming solar radiation, S sub t. I'll talk a little bit later about how S varies with time. And some of this is reflected due to the Earth's albedo, and the rest is absorbed. And the division by 4 is to do with the averaging over the whole of the Earth. And then this is absorbed by the Earth and also from the atmosphere. And both the Earth and the atmosphere then radiate energy away, acting essentially as black bodies. So you get energy flux from the Earth and energy flux from the atmosphere. And the atmospheric temperature is about 242 Kelvin mean. The Earth temperature is 288 Kelvin mean. An energy balance model it literally balances the energy coming out of the Earth, coming from the sun, being absorbed by the atmosphere and being re-radiated from the atmosphere. So if you do an energy balance into the atmosphere, you got the flux from the Earth and the flux from the atmosphere. And if you do that balance, you very quickly get the equation that the 4th power of the atmospheric temperature is a half the 4th power of the Earth's temperature. And if you do that calculation, you get exactly the numbers 242 and 288 coming out in ratio. So that's looking good. Then you have to remember that energy is received by the Earth as shortwave radiation and re-radiated in the infrared, in particular as long-wave radiation. And these radiations have different transparencies. The shortwave transparency essentially goes straight through the atmosphere as about 0.9. The long-wave transparency is about 0.2. And when you do all the kind of balancing out of everything, you get the equation, the first of my 2 equations, which is that the energy coming in from the sun on the left is this number composed of the long wave and short wave transparencies times the radiation coming out from the Earth. And we combine all those into a thing called E, which is the emissivity. And that allows us to predict the temperature of the Earth in terms of these numbers and the radiation from the sun. This is a calculation I do my undergraduates. I even do it when I go into schools with high school students. It doesn't involve anything much more than solving quadratic equations, and gives you a formula which predicts the Earth's temperature based on things you can measure. And if you plug in all the values, you actually get the right answer. And I find that impresses them. Also, you can take the same numbers, same formula, and apply it to the moon, and you get the temperature of the moon, and that impresses them even more. So I like doing that. And you can calculate the sensitivity. It's known that the emissivity or the long wave transparency decrease as carbon dioxide increases. We know carbon dioxide is increasing. So in 2018, sorry, I should have a more up-to-date figure. It was at 407 parts per million, which is a massive rise. Of course, a climate skeptic would say, oh, 407 parts per million, that means CO2 is a trace gas, therefore it has no impact. That's another argument you get, which is nonsense, of course. But knowing the relationship between CO2 and radiative transparency means you can predict the change of the Earth's temperature with how much carbon dioxide you put into the atmosphere. And this is really important calculation. And this simple energy balance model allows you to make a first order calculation of that, assuming nothing else changes. In fact, things are a bit more interesting than that. As the temperature increases, so the ice melts, and as the ice melts, so the albedo goes down. And the graph in blue is a kind of rough indication of how the albedo changes with temperature. So if you have a very cold Earth, it'll largely ice over, and you get a high albedo of 0.7. If you have a very hot Earth, most of the ice melts, well, all the ice melts really, you have an albedo of 0.3. And this albedo relationship increases the sensitivity of the temperature to changes in the emissivity. and that's important and has to be part of our calculation. It shows the kind of feedback loop. Some of the models I've seen for climate then take this one stage further. So I've seen EBMs which then substitute this equation for the albedo directly into the temperature equation, and you then get the equation in the orange. And what's interesting of that is you get this kind of S-shaped curve relating the emissivity to the temperature, which has a couple of tipping points, and the star shows where we are at the moment. And it's things like this which have led to a certain amount of, I think, of misreporting in the press of tipping points in climate, and we've gone too far and we've passed the point of no return. And these sort of come out of these balanced models, but in my opinion, that is pushing these models too far. An energy balance model is good to give a general idea of what's going on, but it shouldn't be relied on really to make dynamic predictions of the way the climate will change in the sort of manner that this picture shows. And the reason for that is the energy balance takes no account of timescales. So in this sense, I call it a bad model. We've had the ugly models. In this sense, it's a bad model. I'm not saying energy balance is really bad, but it's bad for doing things it's not designed to do. So it's bad for making dynamic predictions because it takes no account of timescales for radiation, melting of ice, growth of ice, of glaciers, changes in ocean currents, or the time it takes to have a feedback between releasing CO2 and temperature. And this is where the sort of models which I particularly like come in useful. These are these models intermediate complexity, which start putting in some of the time scales for ice melting, ocean currents, and so on. Look at the way radiation changes and look at the coupling between them. So here's the sort of test I think all EMIC models have to survive if they're going to get anywhere, which is, can you understand the change in the Earth's temperature over, let's say, 1 million years? So here's a graph. In this graph, time goes from right to left. So the current day is on the left, and we go into the past as we go to the right. After a sort of 1 million years ago or earlier, the Earth's climate had a 41 kiloyear cycle with small oscillations. And then around about 750,000 years ago, something happened and the climate changed to having much longer cycles of 100 kiloyears with these are the ice ages and with large oscillations. And this, to my mind, is a really good test of any model because we got good data and it's a nice, clean thing to try to predict. So there are a large number, I counted at least 30 models in the literature when I last looked, which have tried to model this sort of behavior. And I would classify the models as kind of two types. There are those which use classical dynamical systems, which model smooth evolutionary processes, and where Hopf bifurcations are used to explain the transitions. I'll talk a little bit about this in a minute. And then the sort of models which I particularly prefer, which are ones which are non-smooth, which have very differing timescales, which allow switches, in which case we get different types of bifurcation for the transition. One of the main inputs to all of these models is the fact that over periods of tens of thousands of years or more, we know that the solar radiation varies. In the 1970s, everyone got very excited because scientist Milankovitch showed that due to the wobbling of the Earth, particularly the precession, the obliquity and eccentricity changes, the solar forcing, S of t, actually changes periodically over certain timescales as we go back into the past. And in the 1970s, this was hailed as the explanation for the ice ages. Books were written saying the ice ages explained entirely in terms of these Milankovitch cycles. And funny enough, again, going back to my website, people say to me, well, come on, we know the climate's changing. It's due to Milankovitch cycles. Haven't you thought of that? And the answer is yes, but these things have periods of tens of thousands of years, not 10 years, which is what we're seeing. So here's some sort of issues which we try to address when looking back over these million years. If you look at the Milankovitch cycles, the key cycles, in fact, the most important cycle has a period of about 41 kiloyears. And that's the fact that before the mid-Pleistocene transition, about 1 million years ago, the climate was oscillating at 41 kiloyears. I don't think is a coincidence. I suspect that was what was doing it. But now we've got a 100 kiloyear cycle. The eccentricity variation, which is 100 kiloyears, is there, but is very small. So there's a lot of questions as to what's causing the 100 kiloyear cycle. And if we could understand that in the past, we might be able to understand our climate better into the future. And there are three kind of theories. One is that it's entirely forced by the eccentricity. Secondly, that it's sort of synchronized. So there's internal nonlinear processes going on, but just like our body is synchronized to 24 hours by the sun, so it's in some sense synchronized. And the third is that the climate is going to have a 100 kiloyear period anyway due to ice sheets, and that's nothing, it's pure coincidence that it's the Milankovitch. And these are sort of the questions that are being addressed. And I'll try and finish this talk by just explaining my own perspective on this. So here's one model amongst the 30, which is a sort of famous model due to Saltzman and Marsh, published in the 1990s, called the carbon cycle model, which models the climate as three variables: the ice mass, the CO2 level, and the ocean temperature, B, C, and T. They come up with this nonlinear differential equation. I'm not sure why, it's never very clear, with the solar forcing S of T and another forcing which is due to changes in CO2 level due to tectonic plates. And that model you can analyze. And if you analyze it, you get a Hopf bifurcation, and the slow parameter that they vary is f of mu. And so over here, you'd have or here, depending on which model you choose, you have 41 kiloyear cycles, and then you get a Hopf bifurcation into 100 kiloyear over here. And this is the explanation for the mid-Pleistocene transition in terms of Hopf calculation, bifurcation. It's plausible, it fits the data, but there again, the parameters in it are chosen to fit the data. And so we're not really sure whether it's right or wrong. And this is one of the problems with these models. We can't go back in time to test them, and we can't run our GCM models forward in time to test them either. Here is a second set of models, and these are the ones I'm particularly keen on, which I'll call relaxation oscillator models, where basically you have different states in the atmosphere and you switch between these states relatively rapidly. And it's the states that you're in which determine what sort of, whether you're in a sort of glacial state or non-glacial state. And various people, including myself, have worked on these. And a model which I particularly like is called the Pallard and Perrinin model, 2004, or the PPO4 transition model. And this again models the climate using three variables. In this case, it's the total ice volume, the ice volume at Antarctica, and the amount of carbon dioxide. And just to sort of summarize the model, the idea is that the ice volume increases, and that changes the stratification of the deep ocean. And at a certain critical level, the deep ocean stratification breaks down, carbon dioxide is suddenly released into the atmosphere, and the sudden release into the atmosphere causes a warming of the Earth. which leads to rapid deglaciation. And you have two timescales here. You have a sort of 100 kiloyear timescale for the ice volume to increase and change the stratification, and then a much shorter timescale, which is that for the release of the CO2 and the rapid warming. Here's the PPO4 model in mathematical glory. Again, it's three differential equations, but the difference between it and the Schmaltzman and Marsh model is the non-smooth switch, the Heaviside function in the rate of carbon dioxide, and that is a switch driven by this parameter F, which is governed by the total ice volume and the Antarctic ice volume and a few other things. So that's the PPO4 model. And this is a typical kind of prediction from it. Sorry? Yeah. So this is, here time is in kiloyears. I've nearly finished, by the way. In green, we see the forcing due to the Milankovitch. In the purple, you see the CO2. And in A and B, you see the amount of ice. And this looks reasonably like an ice age. If you cheat and make the Milankovitch forcing purely sinusoidal with a 40 kiloyear time period, you get the rather interesting fact that as you vary the period, you can have a coexistence of two types of periodic orbit, which I'd call a period 3 and a period 2 periodic orbit. There they are. There's my two periodic orbits coexisting, looking slightly different from each other, but they're both stable and they both exist. And here's a domain of attraction. So if you start in a certain state in red, you'll end up with the period 3 orbit. If you start in the state in blue, you end up with the period 2 orbit, and you get a transition called a grazing, which is an orbit which causes this kind of switch between the level of carbon dioxide. And if you run the model forward in time, what you find rather interestingly is you can have a type of dynamics where you have the period 2, and then you go through this what's called grazing event, and that changes then to period 3. And that doesn't look too different from the mid-Pleistocene transition. So I'm warmly confident that this is on the right lines for explaining, at least in some simplified sense, what's going on with the ice ages. And if you put in quasi-periodic forcing, which is more realistic, the results simply look more realistic. So I'm going to label a good model. It's not my own model. I've simply studied it a bit, but as a way of understanding what's going on in the past. And the PPO4 model is now incorporated into a number of much more sophisticated climate models as a way of predicting the ice cover over much longer periods in time. So just to finish, mathematical models, I would argue, are the best way to predict future climate and to understand past climate. We have to work with a hierarchy of models to make useful predictions if we want to explore the full range of time and length scales, and also to help validate one model against the other. Crucially, models are only as good as the physics and data that you put into them, and have uncertainty. But I think we should be confident that if we do things right, we do model things right, and we do make correct use of data, then the models do seem to give answers which look close to the truth, and we should trust them, and we should advise our policymakers on that basis. And that I will finish. Thank you very much for your attention. So I will stop sharing now.
Yeah. Thank you so much, Professor Budd, for that wonderful presentation. That would be a guideline for anyone who would like to start mathematical modeling for climate change research. So that was a very, very informative talk from you. Thank you so much. We will be taking up the question answers along with the panel discussion. Meanwhile, I will also welcome Professor Parimal Vyas sir, our Honorable Vice Chancellor, the Maharaja Sayajirao University of Baroda, who has just joined us for this webinar. Thank you so much, sir, for joining in spite of your busy schedule. Sir, we have on the panel almost all the speakers which we had in the last 4 sessions. And they are all experts in the field of mathematical modeling involved for climate change. To the other panelists, let me introduce Professor Parimal Vyas to you. He is a person who is having a dual professorship in commerce as well as Faculty of Management Studies. And he has, under his able leadership, the university has raised to new heights. He has been instrumental in introducing number of new centers, new programs, new offices, and the Institute of Climate Change Research is one of those offices. We have a very strong support under his guidance and vision, and he's always there to encourage us in all our endeavors. Sir, can I request you for your address, sir, please?
Namaskar, good evening, and at the outset, let me extend 5th September is a very, very important day in the history of India. We are celebrating today, 5th September, each year as the Teachers' Day. And what a wonderful, coincidence that I know a couple of experts, they were there earlier also in the webinar. I believe Professor Danesh is responsible, who is our director of the Office of International Affairs. I'm very happy because in a short span of time, Institute of Climate Change Research has started conducting webinars. Maybe this is 4th or 5th webinar, if I'm not wrong. And what I would like to share with all of you is that the Sarvapalli Radhakrishnan, he was the president of the Government of India. He was the second president of our country, and his birth date is celebrated as Teachers' Days in the entire country. Today you find, in fact, I've just concluded the webinar which was organized by our government of Gujarat, Department of Education. Likewise, today at the national level, there are webinars and talks and number of activities, but they are all happening online because of COVID-19. And I'm not sure, but one major development that has happened in the India is that on 29th of July, the cabinet of the Government of India has approved what is now known as National Education Policy. After 34 long years now, the Government of India has now approved the policy which has been implemented. One of the major change of that National Education Policy now, which now will be implemented, phase-wise, is that Ministry of Human Resource Development now has been renamed as Ministry of Education. Now, this is a major change, and there are other structural changes. But when I relate the new policy with the Maharaja Sayajirao University of Baroda, this National Education Policy has a very strategic and clear emphasis on multidisciplinarity. Now, this is very, very important. Let me request all of you to note, all the educational institutions, all the universities, currently you find there are central universities, states universities, deemed university, private universities, all of them now they are put into one umbrella. Now that is one major change. Second major change is that all the universities would be divided into 3 parts. Number 1 would be research intensive universities, the other would be teaching and research intensive universities, and third would be autonomous colleges, autonomous degree giving colleges. Now these are the 3 major changes, and this policy is student centric, and it puts a very heavy emphasis on what we call it as multidisciplinarity. We have Institute of Interdisciplinary Studies, and I'm very happy to learn. In fact, for last couple of years, we have been trying to, promote interdisciplinary research. And unlike, we talk about science, technology, this national education policy focuses on liberal arts. It is very interesting. Now the policy emphasizes upon that scientific temper is important, but at the same time, you really need to also learn, various other, disciplines, fields, areas. Plus, there is a very clear and strategic emphasis on the various kinds of skills development. Why I'm discussing about these is that our university is, we would be aiming to, take our university on a newer heights with reference to what is now being termed in the policy as large multidisciplinary research universities, where you would find that we have 100 plus departments with the faculties of performing arts, fine arts, social work, management studies, family and community science. These are my faculties, in the humanities and social sciences, and we have a very strong, presence of faculty of science, faculty of technology and engineering, and few other faculties which would be covered under the pure science, pure and applied sciences. Another small request which I would like to make to all the experts, because I think I met Professor Machi last time also. He was coordinator. So welcome back again. I could realize that, yeah, he's also today with us, and Professor Colin and Dr. Tuomo and various other. I won't take one name on a one-to-one basis, but I'm very happy that all of you as usual, Professor Dhanesh has become a hub to bring all of you. And we can't think of a life without mathematics. That is very very much important. But I also take as an Indian as a pride that, okay, that big zero has come from India. I think that credit is with Indians. The purpose that I wanted to be with you, I thought I would not be able to make it. But thank God that webinar ended because Honorable Minister of Education was addressing. So in fact, I was not sure whether that program would be over or not. As a part of protocol, you have to be with your minister. But my request to you is that irrespective of COVID-19, it would get extended for a couple of more months. But I want all of you, to guide the Maharaja Sayajirao University of Baroda. For example, climate change, my expectation is something very different from this Institute of Climate Change and Research. It's not just webinars or some kind of research projects here and there. See, the biggest challenge which I understand is that we will have to sensitize all stakeholders. Now, this is the challenge before all of us. We will have to carry out our research activities, and then that would be on. So that research exchange, maybe of the research scholars and the academia would continue. I want you to guide us. And let me tell you, I'm very clear in terms of my expectations. And what is that? Can you guide Professor Dhanesh and Dr. Sanskruti, who is the director of Office of Alumni and Donor Relations, and now I think she's also playing the role of a director of this Institute of Climate Change Research. We want to launch certain online courses, be it a certificate courses, be it certificate. I would be very happy if you can help me to design 2 credit 30 hours course. And I think you can very well help us. You can guide us. We can design the online modules supported with the content in form of videos and all other stuff. I think then probably whatever efforts that we put in these kind of webinars, if we systematize it, bring the scholars who are interested in climate change, those who are interested in mathematics, if we can bring them together over a period of time, what I believe, because I teach management, I always believe in successive planning. And that successive planning can happen because what happens here right now in this webinar, you have all your experts, all of you, with all of you where you are really interested in making use of mathematical modeling in resolving the problems that the entire world is facing in terms of climate change. Can our university, with your support, with your guidance, with this institute, we want to become a hub in our country. And let me be very honest, I hope Sanskruti will agree with me that, in our country, we are going to set up what is known as National Research Foundation. Government of India has already allocated 2,000 crore rupees for that. And Government of India is now committed to spend around 6% gradually of GDP. Now that is the kind of an allocation. This is the kind of an emphasis that Honorable Prime Minister Narendra Bhai has on education. And one more thing which I would request all of you to note, that for now research activities, for whatever support, earlier only state universities were getting some support, central universities were getting support. Now at the national level, Government of India has created level playing field. Whether you are from private university, in fact, that distinction is now over. I should not say that. There are no categorization of universities in this country. Any teacher, irrespective of any academic institution working in any part of the country, will get the financial support under NRF, on the basis of the strength of the proposal. And I wish you please help Dr. Dhanesh and the team of research scholars and other teachers when they want to carry out research in the area of climate change, using mathematical modeling. I believe if we can do that, probably we can, to me, it would be a turnaround strategy. So I am looking forward, the purpose that I thought I should share with you, I am looking forward for a kind of an academic, support. I'm looking for a kind of a collaborative support in terms of research publications, because I think I'm not a man of climate change, but I know that in fact, the biggest challenge that I find in climate change is we really need to carry out the impact studies. The databases are available, but those impact studies are not happening. Now, I think how it can happen. We have a very powerful Department of Computer Science and Engineering in my faculty. We have a Department of Civil Engineering, which is very powerful. Sanskrit is a part of it. We have a Department of Mathematics, plus we have a Department of Applied Mathematics, to which Dhanesh Patel is, former head. So there are opportunities. I think I'm quite excited, and you must be feeling my excitement. Probably till now in India, research means it's only science and technology. I think now there is a major breakthrough. That emphasis will continue, but then also there will be an emphasis on humanities and social sciences, what we call it in our terminology as liberal arts. There will be emphasis on yoga, there will be emphasis on culture and various other disciplines. I will not take much of your time, but my humble request to you is that now there is an opportunity for preparing certain proposals which will be of an interdisciplinary nature, maybe within the country and outside India. Climate change is not that only we are facing. I think the entire world is facing this problem of climate change, and it differs. I'll tell you just one small example which I'll give you. If you look at the ongoing monsoon in the state of Gujarat, Sanskruti is an expert, I am a layman, but one very interesting phenomena which we observed in our state, there is one part of the state which is known as Kutch. If you look at the rainfall pattern, this time they have received more than 300% monsoon. This is, I think, history. Maybe we fail to understand, and we are in fact experiencing a very dramatic and interesting changes in the pattern of monsoon in our state of Gujarat. I think that would be a very, very important area of research, that how it has happened and how do we go about. In another area on which I wish you can guide us is that because I teach management, I understand that India is blessed. God has blessed us with the resources, but we have not been able to preserve it. Water conservation, like energy conservation, I think is a big area. In my university, probably we have conducted water audit, because we want to sensitize that each drop of water is extremely important. And I really feel, with pain I'm sharing with you, that these heavy monsoon flood that you find in some part of the country, we have not been able to take care of the water. I think that is so precious to all of us. What we really need to, I think it's collective responsibility of people like us to see to it. not only we do research, but we sensitize the generation and the generation that would follow in near future. I apologize that I should have joined. In fact, I told Professor Dhanesh that it would be difficult for me because, right from 3 o'clock, this is the 4th webinar I'm attending. But I'm very happy to see some of the faces which you are there. I request you on behalf of the university, please keep your blessings. Maybe I will always try to be with you, but sometimes it's not possible because of my personal constraints and the commitments. But I wish we are all for a common cause to make the world the most beautiful place to live in. I think that is your purpose, and that is the purpose of each and every one of us. So I welcome all of you, and I appreciate your support and guidance to the university. On behalf of university, I convey my sincere, thanks to each one of you. And let's pray together that the country and the whole world would come out of this pandemic, I think, in near future. And we would be able to invite all of you one after the another, maybe in some such other academic event where we can spend time together and can make a meaningful contribution. Thank you very much for a very patient listening. Namaskar.
Thank you, sir. Thank you so much for joining us in spite of your busy schedule, and your blessings and suggestions are the backbone for our activities. You were just mentioning about the webinars, so I'm glad to share that we have conducted so far 16 webinars starting from 25th May. 8 of them were independently under the banner of Institute of Climate Change Research, and we have 10 in collaboration with the Climate Change Department, Government of Gujarat as the knowledge partner. And we have many more lined up, so we will be.
But Sanskriti, please prepare a small report, and we need to, send it to Government of India, and we need to send it to Government of Gujarat, because they really want to understand what activities are happening in the university. So that's very important.
Yeah, sure, sir. And in fact, with Climate Change Department, I'm glad to share that we are also in the process of preparing some material where we can start a webinar series for school children.
Okay, I mean, that is great. In fact, that is Sanskriti, that is the need of an hour. I always believe that we all understand. But then if you start, I would say not even school, I would say start at the nursery level. Let us make our child understand that tree is more important than temple or mosque. I think that we will have to, and then we will have to, create a kind of an emotional connect with all the natural resources, be it tree, be it water. I think if we can create that civic sense, probably after 10 years, I would say that we would be able to bring about a kind of a behavioral change and the outlook towards the natural environment, and and I think then probably the purpose of your institute you would be able to realize. So my best wishes to you also. That's great.
Thank you, sir. Thank you so much. You've always been a pillar of support in all ways. So thank you so much, sir. Thank you once again. We have, as I had mentioned, that we will be having a panel discussion today, and all the speakers as well as the panelists will be open for questions today for the panels. So, sir, you can also join in if you are free.
In fact, I would extend an apology because still there is one more event for which I will have to join. See, it is unfortunately, it is like, it is Teachers' Day, so there are a lot of expectations from many people. So as I said, from 3 o'clock, this is the 4th event. One event is still piled up. We have on 7th, sir, we have a very important event taking place at the national level. Honorable President of India and the Minister of Human Resource Development, the Prime Minister of country, and all other cabinet rank minister. There's a very big event which is taking place on 7th of September, and then certain other assignments have been given to our university. So I'm in a process of that entire coordination which has to happen from the university. So that is why otherwise I would certainly spend time with all of you. But before in fact, I would request you to allow me to, leave the meeting, convey my best wishes to you, and look forward for some another opportunity where we would certainly spend some more time. Meanwhile, you please, if anything, you via Sanskriti or via Professor Dhanesh Patel, maybe, or my email is also available. you're most welcome, sir. It would be wonderful to, stay connected with each one of you. Thank you, sir.
Yeah.
Thank you.
If I may, please before you leave, Honorable Vice Chancellor, make a small announcement.
Yeah.
This has been a pleasure indeed, being part of the community for a long time, visiting Baroda several times, and it's always been helped by Professor Danesh Patel. He initiated all of this. So I wish now to announce that Professor Danesh Patel has been appointed scientific advisor to Argonaut Limited.
Oh, that's great.
Oh.
So that's he's been energetic not only in science and applied mathematics, but also in helping us try to build a business presence in Gujarat.
Oh, that's great.
Including, for example, twice meeting your Prime Minister Narendra Modi while he was still Chief Minister of Gujarat.
Please. Yeah.
So thank you very much, Danesh. Welcome to your new role. And
thank you.
Yeah, let's move on to the.
And my best wishes to Danesh ji also. Danesh ji, maybe I could understand little, but then you understand. It's a very, very important international recognition that you're getting. My best wishes to you for that role. And Sanskriti, let us see to it that it reaches to all stakeholders via our communication cell. Thank you.
Sure, sir. Thank you. So thank you, Dr. Kaurane, for that important announcement, and congratulations, Professor Danesh Patel, sir, for this new assignment. So the floor can now be open for question answers and panel discussions. So I will request all the panelists. Yeah, that's exactly what I was saying. Shall I read out the questions first, and then we can have a cross discussion, or?
Sanskriti,
Yes,
see, I mean, the summary of the lecture will be by Professor Tomo. Or you are giving it there?
No, sorry. Let's move on to the panel, Danesh. I will think we skip it now. It was an excellent presentation by Chris, Professor Judd. It shows in a remarkable way how even quite simple mathematics can be highly relevant to solving maybe the most crucial question, that how much of the climate change is anthropogenic, how much of that is caused by natural causes, and how they interlink. I was very impressed by especially your presentation of the PPO4 equation, that it really seems to be that there's a very massive underlying reason to why this is so critical to us to understand that right. And although having spent much of my career in climate science, it's the first time I heard about the model. So thanks, Chris. Marvelous.
Yeah, thank you, Dr. Tomo, for that summary. Sir, we have a few questions. Should I read out the questions? One of the questions is that what is the difference between climate variability and climate change, and how can we use the mathematical models to distinguish between them? Would you like to take that question, sir?
I kick off. I mean, I would say climate change is what we're seeing at the moment. So I would think of it as what is the immediate impact of what we're doing, like carbon dioxide and so on, to the immediate climate. How is the climate being changed by human activity? Climate variability, I would say, is what's happened over the last billion years. How has the Earth's climate varied, and can we understand the way that's varied? And over the periods of time, we're looking both at the Earth and also at the Sun. So climate change is what we're seeing now. Variability is everything over the last billion years or so.
Yeah, thank you. One of the question is that can there be any model which includes every aspect of the real world? I think you have answered that, but if you would like to take it.
Yeah, the answer is it's a simple no.
Yeah.
If so, it's not a model.
It's not a model. It's not a model. If it contains everything, it's not a model. A model is a simplification of the world to try to understand it.
Yeah.
Then there is a question that can animal and bird noting future climate be made use in prediction of climate change, or is there any research based on that? The question is from Dr. Narhari Chaudhary.
I don't know of any work on animal and bird behavior.
There's certainly, you can look at changes in animal behavior as an indicator that climate change is happening. So it's one of the proxies, and a lot of work's been done on this, studying changes in vegetation, changes in where kind of the location of animals. So animals, for example, in the UK, birds are now nesting, never nested before, and a lot of people do work in that. So I think it's a clear indicator that something long term is happening.
Then there has been a lot of discussion, especially during the lockdown period in India, regarding the impact of the COVID-19 on healing of the earth. So there is one Dr. Pradeep Desai who would actually like your comments on that. Has COVID-19 helped in cooling down Mother Earth from the adverse effects of climate change?
If I make one view on this issue, it's simply that we are getting a short respite from much less traveling, less air traffic, in general, maybe less physical activity and more digital, virtual activity, as we witness here. So some part of that hopefully will remain with us even after the epidemic is over. And maybe that will help in a little way to somehow reduce carbon emissions and thereby slow down the dramatic climate change. But we, of course, may be already beyond this tipping point that those models that Chris presented show. So in that case, we will not know until quite some time. But definitely, I would call this like a secondary blessing from the pandemic, that we've learned that we don't always have to travel, and we can have nice international webinars as now. And that applies to our business as well. We work in 30 countries at Arbonaut, and we haven't been traveling for the last 7 months to any of them, but we seem to be getting more business now despite this. So I hope something changes in other business areas likewise.
There's been an interesting impact. As I say, I've been looking a lot at the impact of climate change on energy. And since lockdown, the UK has not burnt coal to produce its electricity. So that's been a huge impact.
Remarkable. Yeah.
I would actually add to this discussion that we realize that we are responsible for climate change, because when there were publications or news items like change in the temperatures and other impacts, positive impacts of COVID-19 on climate change, then there were people who were under the we as humans are responsible for climate change. But then this COVID lockdown actually proved that we are responsible in a way. So that was, I would say, a learning lesson for many in a way. So the floor is now open for discussion. Dhanesh sir, I will request you to take the lead, sir. Sir, your mic, please.
Professor Ratish, you might have some questions. Yeah, please go on.
Okay, I think I'm Ratish from IIT Kanpur. Chris, it was a wonderful talk. It was a learning experience. A lot of nice things that you brought in here. I've been listening to some of these talks, and it was a wonderful experience. So my question is regarding the use of hierarchy of models for the full range prediction versus model reduction. So I do understand this model reduction as a mathematical concept which has been used for simplifying complex models to get the solutions. In a way, we can probably integrate that with the use of hierarchy of models. I would like to take your comments on that.
Well, my comment is that you do need all of them. So the GCMs are not able to predict climate over thousands of years. And so if we want to understand climate variability, using the term, you simply can't use a GCM. You have to use another model in the hierarchy to do that. And then those models that you can are doing that can then be checked against the GCM, so they can kind of test one against the other. So I think the two do work together. To look at climate change, in other words, look at the sensitivity. So if you change, for example, COVID, emissions due to COVID, I wouldn't want to use an intermediate model. I'd want to use the full model so I can get a much better understanding of the real sensitivity. So I see that's how it works. Another thing is, from a purely mathematical point of view, if I want to try to kind of get a mathematical understanding of something, I can't do it with a full model. It's just too complicated. Whereas an energy balance model, you can actually see how things change as you change parameters and get a feel for things. And in terms of educating high school students or whatever, it's much easier to work with that model to kind of see the impact of things. I mean, one of the big problems of GCMs is that there's so much output from, and there's so many variables, it's really hard to see what the effect is of changing one thing on something else, especially if you have to wait a week before you get the answer. So I see this as, you know, a hierarchy, but we see this in many other aspects of life. It's not just in climate models. I mean, there's many other things that you might want to model, industrial processes, for example, or going right back to Newton, the kind of models for the solar system. So, you know, this is how mathematics and the real world have interacted with each other for a long time.
So thank you. What is there a way that we could integrate the information from the EBMs into GCM in a way that we could make GCM, because GCM is going to give you the leverage in terms of resolution, but definitely, as you rightly said it, for historical information over long range, it is not the right thing to go about. But the integration between these two, what I would like to know, what is the kind of the state of art in integrating this, because one is for a long range, other is for high resolution, but integrating this, so where do we stand?
Well, we use one to test the other. I mean, if a GCM doesn't have an energy balance in it, then something is basically wrong. So given that you can't easily test a lot of things with the GCM, because you can't wait for 100 years, this is part of the internal testing process that you have to use. I mean, the other panelists might comment differently, but this is.
I would like to share my view, especially when you're using GCMs. People use a lot of nudging. The nudging information could come, a lot of historical information. Now it could be fine-tuned from your other models, which otherwise the nudging data wouldn't give. I thought, what do you think? That could be one way of integrating a more useful information into GCM.
Well, absolutely. So for those of you not familiar, nudging means you have some sort of a priori knowledge of what you think should do, and you use that to weight your solution. It's a sort of Bayesian method. Well, essentially, that's what we do.
Okay.
And that is definitely what the Met Office is doing to stabilize its forecasts.
Thank you.
All right. Dr. Amit, since you are from data assimilations, so if you have any questions with mathematical modeling, could you please share some your views to all panelists, please?
Yeah, Chris, I enjoyed your talk. It was quite beautiful. Especially
by the way, I love your papers.
Sorry?
I really like your papers.
Oh, thank you. Yeah. So actually, I had one question about, in terms of this hierarchy. You showed this beautiful, very nice slide about how we went from 70s, 80s, 90s, and until now, how different parts of the model went into being, so to say, the core parts of it. Yeah. Somehow your 2010 plus column, there was nothing at the bottom. So do the climate scientists actually have a feeling that they have really included whatever needs now?
Yeah, I apologize. It was slightly out of date slide. I mean, one of the big questions of climate modeling and is cloud formation, and a huge amount of work's being done on that. And the really annoying thing about clouds is that you have no historical record of clouds other than human observations. You know, you can't look back a million years and see what the clouds were. So certainly a huge amount of work's being done on that, to my knowledge. And another area that I'm involved with is understanding more about the variability of the solar radiation. So we know that the sun's radiation has changed quite a lot over the last few thousand years, and trying to model that better. So yeah, I apologize. It was a bit of an old slide. I should update the slide.
No, that's fine. Yeah. Yeah. And I guess in terms of thinking about data assimilation problems, there is a very interesting issue about how data assimilation can be actually used to understand climate timescales, because these are much longer timescales. The data we have are on a much smaller timescale, and of course at a much higher spatial resolution. So incorporation of data into climate models in order to make climate timescale predictions is an interesting mathematical issue, I think. And if any of the panelists have anything to say about this, that would be useful.
Yeah,
there are some efforts in that direction, but I think not sufficient has been done until now to actually be able to use data in a rigorous way for climate predictions.
Yeah, I mean, that's a terrific point. I think the best data I know from a climate point of view would probably be ice, data of sea ice.
Yeah.
And certainly you can compare that with the predictions. Yeah, I mean, data assimilation, of course, is really powerful if you've got lots of data that you can feed in a constant way, and you can't do that with climate. But still, we can look at that.
Okay, thank you, Dr. Amit. Now, Tuomo, would you like to say something? Would you like to focus something on these lectures related to forestry science? Last time it was a question for you that what kind of mathematical models you are using for your company. That was a question last time.
Yes. All right. But in some sense, I'd like to join the climate modeling community here, since much of my past career was in that direction, data assimilation included. So kind of a gut feeling that seems to come evident from a lot of work in these areas is the challenge that when to Professor Rajesh Kumar's question, that hierarchical models, that somehow the devil lies in the interaction between the different scales. And we have this situation that things which are relevant for weather forecasting and GCMs are quite different, and they kind of cancel out on the climatic scale. Whereas the phenomena that are relevant for climate, let's say ice, especially Antarctic ice dynamics and that sort of scales, they are so minuscule on the weather scales of weeks and months and even years, that there's no way we can calibrate. So this kind of a transition of scales and dominant local singular vectors, let's say, or dominant modes, nonlinear modes like soliton type of solutions that you might have, they change so dramatically, and it's necessary. I would like to use a marketing slogan here. It's necessary to oversimplify. So the most dangerous thing you can do, and somehow most useless, which often applies to scientists in geophysics as well, that you try to be as complete as possible in every model. That's totally wrong, because indeed you're like really missing the point. If you try to solve every detail, you will have so many parameters to calibrate that there will never be an adequate statistical basis for the calibration of those in a data assimilation process. I learned that firsthand 40 years ago with ecological modeling, where we had so many species in water quality models, And we took the values of the parameters from established literature, good handbooks of laboratory experiments that related to the biochemical reactions, and it was useless. You know, we were able to get maybe the three most dominant state components of the state vector somehow calibrated, and the rest were just noise. And I think this is it's not a bug; it's a feature of the nature as we see it. So that's why I found, Chris, your choice of model so insightful, that it seemed to find that one dominant thing, the Antarctic sea ice and the stratification of the oceans, that you can capture in a system of ODEs rather than going to the full-scale GCM. So insightful that we should try to go for this kind of insight that often has to come from some kind of gut feeling. It's really hard to do systematic modeling or modeling studies. But once you have this, then you could try to test that with, for example, whatever time series we have from sea ice to try to see if those are produced, and then see if it's possible to introduce the relevant balances, mass balances or energy balances into the higher resolution, shorter term models. And then of course, eventually, whenever we are down into I used to work at ECMW for the reanalysis effort as well. Now we have the last century or so with relatively well interpreted description of the past weather. When we can come down to that kind of time scale, then we have an adequate source of data to do our data assimilation with hindcasting. So it's been really nice, and of course, in some circles, I hope it shows the importance of good mathematics, the right kind of mathematics, even theoretical mathematics in making sense of all of this. So this is Sanskrit to you as well. It's climate modeling is not only about the numbers, the facts, the geophysics, and so on. It's definitely also about understanding the structures that dominate the phenomena you're studying. Thank you.
Thank you very much, sir. Now I have a question to Professor Colin, and yeah, just a minute, Sanskritik.
Sure, sir.
Only 1 minute. I have a question to Professor Colin and Chris Bird. Let's see, there are many students right now, many students, master students, it's academic question, research students, and some NGOs people are attending this webinar. Now, interestingly, the question is that suppose some engineering people want to do mathematical modeling in climate change, or let us say surface runoff, let us say rainfall, so surrounding hydrological cycle. So how to motivate those students in this area? Because the question is, they have not that much knowledge in that area particularly. For example, as Tuomo sir said rightly, that they are using statistics. Yeah, in some statistics, several subjects are there. Time series analysis in mathematics also, PDs, ODs are there. How to motivate the students? That's my question for the students here, please. Colin?
Start?
Oh, well, I sort of start. So I do have a couple of my own students that are working in flooding work, if that's what you mean. So I mean, we're doing it largely by doing computations using the shallow water equations and finite volume methods. So they're actually getting their hands dirty, and this is the people that are particularly interested in actually sort of funding this are the insurance companies that want to know what the effect of climate change is going to be on their premiums. So that's kind of motivating in a way, I hope. And we're collaborating quite a lot with the Dutch, who clearly have a strong interest in whether flooding will affect their country due to climate change. You know, any low-lying country is going to be very interested in flooding. So I think that's pretty motivating from the Dutch point of view. Colin?
Well, the only thing I was going to go and say is that having listened to Chris's talk, which I thought was absolutely fantastic, I think the thing that should come over to any master's student or undergraduate, that what you need to do is to understand your mathematics. You need to learn mathematics, you need to learn your statistics, and then you need to go with those tools. You can then go and talk to people who have raised the interesting practical problems and use your talents to do it. At the end of the day, you need the underlying mathematical knowledge and skills in order to be able to go and attack these really difficult problems.
Yeah.
Thank you, sir. Yes, Samskruti, go on.
Sir, my question to you was that while going through the publications, research publications, we observe that a lot of research can be done for larger areas, like taking the entire country, India, or large river basins like Ganga Basin or Yamuna Basin or Brahmaputra Basin or Kaveri Basin or Narmada Basin. But then when we need to carry out research for smaller areas like say Vadodara city or Vishwamitri Basin, these models actually fail over there because they are, if we go for statistical or dynamic downscaling for these models, the area, geographical area of the city is very small. So how do we deal with the models for such kind of problems? Because even if we go for downscaling, the entire area would be less than one grid. So what would be your guidance for carrying out research in such cases?
So maybe to trigger the discussion, I will just share with this question I have been recently faced. I think people were asking me this. And one of the things that we have taken an analogy to what happens with respect to image processing, we were looking at that. We thought that the super resolution, which has been a big solution in the context of image processing, that has been currently being experimented. Exactly for a scenario like what Samskruti is asking, I think we have experimented along with IITM people there. And the students who had done some internship exactly on this kind of initiative were trying to focus on localized rainfall, and they want to get a good prediction on that. And super resolution did sound promising. This is just a sharing information. I think other experts may be able to throw more light. Super resolution approach was one possible way of looking at it.
I mean, again, what we're doing is rather similar. I mean, if you want to look at local flooding, you can get the general picture of the weather from the general weather forecasting models, but then we build a separate shallow water equation model with high resolution for the area. So, and we work, for example, with our local water company that are interested in the impact of flooding on sewage. And you have to just use a high resolution model there. I wouldn't say it's particularly pretty, but it's important. And you might want to do the same for tsunami modeling or something like that. So I just come back to say shallow water equations with lots of careful, incorporation of local topography and bathymetry and stuff.
I think if you have any suggestions or any questions, please go ahead. And then I think Mati will discuss the final ceremony. Samskruti. So I think this is over. Any questions more? Colin, sir, would like to say something?
Oh, I think it's been a very interesting discussion we've had here. Some really insightful stuff.
Thank you very much, sir. Thank you. Samskruti, now we have to hand over to Mati. Professor Mati, now you give your closing remarks, and then Samskruti will give the.
I will be very, very short. It was excellent talk, and all the relevant remarks have been made. If we would have one more hour time, I would like to discuss about this conspiracy theories and climate denials and all the false information that's going around. But today, now, no time for that. So it was enjoyable, really enjoyable. And now I have a slightly smaller problem to attend to. Instead of climate change, I have to do a diaper change. So thank you very, very much to all of you, and have a nice day.
Thank you, Martin.
Just a minute, sir. Now there is a vote of thanks, sir. Please, yeah. Vote of thanks, yeah, please.
Okay, so thank you so much. I will thank all the panelists and the speakers for all the 4 webinars. Professor Chris Budd, Professor Colin, Professor Tomo, Dr. Amit Apte, Professor Mati, Professor Ratish Kumar sir. Thank you so much for accepting our invitation and joining us for this series of webinars. I will just share that when we had proposed the formation of Institute of Climate Change Research, the idea was actually to bring all the stakeholders who are interested in the research in field of climate change on one common platform so that we can have collaborative research, because each person would have a huge database collection in their own sector. But then if we try to create correlations between the two, it would be a more meaningful and a more applied research. That was the whole idea when we had proposed the Institute of Climate Change Research. But in the very nascent stage, I mean, just after it was formed, we had this pandemic and we entered into the lockdown mode. So we thought that we shouldn't stop at just being a proposal and an institute on paper. So we initiated this series of webinars where we tried to bring people from different backgrounds so that we can spread a word about the different aspects of climate change. So like Dhanesh Patel sir was mentioning that this series of webinars are being attended by a number of people from varied backgrounds, because we have people who are working in food security and climate change. We have people who are working in health impacts and climate change. We have people who are working on impact of climate change on economy, and many others, besides of course the effect on temperatures and rainfalls and other meteorological parameters. So, and then there are young researchers who will be motivated from these series of webinars to pick up the threads from here and carry out some research once they join their masters or their doctoral programs. So this was a very, very interesting session, series of 4 webinars, I would say, because I personally, we have a team of research students who are working under me. And I personally believe that mathematics is the heart for climate change research, because without that, we cannot move ahead in this particular field. So that's the reason why this was a very informative and very interesting session for the people who are into core research in the field of climate change. So I will once again thank all the speakers and the panelists for accepting our invitation and joining us for this webinar today as well as in the previous days. As you have just witnessed that Professor Parimal Vyas, our Honorable Vice Chancellor, has been very, very supportive, and he is like a backbone for all our endeavors. Silently, even if he is not present in all the webinars, we still have his support and cooperation for all our activities. So I will take this platform to thank him for all the support. I will also acknowledge the role of Professor K.M. Chudasama, our registrar, who is also equally supportive, and the members of the Senate and Syndicate who not just took up this idea of forming the Institute of Climate Change Research, but then also motivating us to carry out various activities and look forward for various collaborations with various institutes across the globe through this opportunity. So I will thank all those people. I take this opportunity to thank Professor Dhanesh Patel, the Director for Office of International Affairs, who has actually put us across and brought us together for this series of webinars. So thank you, sir. Thank you for all your efforts and support. Thank you for collaborating with us for this series of webinars. This webinar series has been supported technically by the communication cell of the university. So I will thank all the members of the communication cell as well as media management group of the university for spreading a word about it and helping us organize this on this platform, as well as webcasting it live on both the Facebook pages of the university. So thank you, Chirayu, thank you, Achal, and all your team members for this. And the press and media has also been interested and has been covering our webinars over here. In fact, I have been getting calls since afternoon, but I said that I will be giving you the details only after the program is over. So I will also acknowledge the support of the press and media, because they are the ones who are spreading the information to the common people, those who are reading the newspapers. Newspapers are also one source of learning in a way for the common people. So thank you, press and media, for covering our programs and helping us spread a word about the climate change. And most importantly, our enthusiastic participants who have been with us right from the first webinar, and their continued support is what we seek in the future as well. So keep visiting the Facebook page of ICCR MSU, Institute of Climate Change Research MSU. Keep liking it, keep sharing the details which we post over there, so that we spread a word about it. So once again, a big thank you to all of you. Good day to all.
Thank you, Colin. Thank you, Colin, once again from our side. Tuomo, thank you very much. Ratish, thank you very much. Professor Chris Bird, thank you very much. Dr. Amit, thank you very much. And Professor Yarno also, thanks. Of course, he's not present, but I give thanks. And thank you, Sanskruti, also. That's all. Thank you very much.
That was
Namaste,
Thank you
good day
very
to all.
much, Ganesh.
Yeah.